Before we plunge into today's material, now that you've found us, subscribe and turn on notifications by clicking the bell. There is just no need to miss out on any upcoming deep dives, because today we are going somewhere truly extraordinary.
Yeah, it is. It's the absolute bleeding edge of where biology actually meets computation.
Right. And before we get into the nuts and bolts of how this actually happened, I really want to specifically welcome all of you out there who are fans of Dr. Alex Wissner-Gross.
Oh, yeah?
Especially those of you who religiously follow his brilliant contributions on Peter Diamandis' YouTube series, Moonshots. We know exactly why you're here.
You're looking for that highly specific intersection of, supreme intelligence and raw futurism.
Exactly. Today's deep dive is absolutely custom tailored for you. So our entire mission today centers on a groundbreaking post from Dr. Alex Wissner-Gross's Substack, which is called the Innermost Loop.
Right, the post from March 7, 2026.
Yeah, March 7. And the title is simple, but it carries, just an unbelievable amount of weight. The title is The First Multi-Behavior Brain Upload.
Which is wild. That phrase alone, brain upload, it has been the absolute holy grail of theoretical computer science and neuroscience for decades.
Decades, yeah.
It's the kind of thing that has always been safely relegated to science fiction.
Because let's set the stakes for a moment here.
Yeah.
When people usually talk about the singularity, that horizon where technological intelligence outpaces human comprehension, they are almost exclusively talking about artificial minds.
Right.
We're talking about large language models, sprawling neural networks, reinforcement learning, AI that just gets smarter by crunching endless petabytes of text or video.
Yeah, algorithmic intelligence.
Exactly. But today, we are completely abandoning that paradigm. We aren't talking about artificial intelligence. We are talking about whole brain emulation.
Which requires an entirely different set of, mathematical and physical architectures.
Mm-hmm.
You aren't training an algorithm to act smart. You are recreating the physical hardware of living mind in a digital space.
Copying a biological brain.
Literally.
Neuron by biological neuron, synapse by synapse. You're capturing the exact messy, organic wiring of a living creature and actually booting it up like software.
Yeah.
And according to this source, a company called Eon Systems PBC has officially done it. Okay, let's unpack this, because I don't just want to announce that they did it and move on. To genuinely understand the sheer magnitude of this milestone, we really have to look at the mechanics of how you even begin to digitize biological tissue.
Well, you have to start with the map. And the foundation for this specific breakthrough, it actually comes from a major milestone achieved back in 2024.
Right.
This was a paper published in the journal Nature by Eon senior scientist Philip Hsu and his team of collaborators. And they didn't map a human brain, obviously, or even a mouse. They mapped the entire adult brain of Drosophila melanogaster, the fruit fly.
Wait, a fruit fly brain is barely the size of a poppy seed? How do you even begin to map the internal wiring of something that microscopic?
It is grueling work. They do it by meticulously cutting the brain into slices that are, fractions of a micrometer thin.
Wow.
And then scanning each of those slices with an electron microscope. After that, they use software to stack those millions of 2D images back together into a full 3D volume.
Just painstakingly rebuilding it layer by layer.
Exactly. It's an agonizingly slow process. But the result is what we call a connectome. Specifically, they use the FlyWire connectome for this, and the scale of it is just staggering. This computational model contained more than 125,000 individual neurons.
Inside a poppy seed.
Inside a poppy seed.
Mm-hmm.
And those 125,000 neurons, they're connected by more than 50 million synaptic connections.
50 million?
Yeah, 50 million discrete microscopic gaps where one neuron reaches out to communicate with another.
Okay, I have to push back on this a bit, because a map is just a map, right? If I hand you a hyper-detailed architectural blueprint of a skyscraper, including every single wire in the electrical grid, you still don't know what the building actually does.
Right.
You know where the wires go, but you don't know if a specific switch is designed to turn on the lights or, trigger the fire alarm. Just tracing the physical connections of 50 million synapses doesn't actually tell you how the fly thinks.
And that is the exact hurdle that stopped connectomics in its tracks for years. You are absolutely right. In the biological brain, neurons don't just touch each other and exchange generic electricity. They communicate across those synaptic gaps using highly specific chemicals.
Neurotransmitters.
Exactly, neurotransmitters. And some neurotransmitters are excitatory, meaning they shout at the next neuron to fire its own electrical pulse. But others, like GABA, are inhibitory. They act like brakes, telling the next neuron to stay quiet.
Right, like dopamine or serotonin in humans.
Exactly the same principle.
Yeah.
But if you just have the electron microscope map, you can't see the chemicals. The chemicals wash away during the preparation process.
Oh, of course.
Yeah, so you have the wiring diagram, but you have absolutely no idea what signals the wires are actually sending.
So how did the 2024 team solve that? I mean, if the map is blank when it comes to the chemical language, how did they build a functioning computational model?
Through a stunning application of machine learning. The AI wasn't used to mimic the brain, which is how we normally think of AI. It was used to read the physical structures that the electron microscope left behind.
Read the structures. What do you mean?
See, an excitatory synapse and an inhibitory synapse actually have incredibly subtle physical differences in their shape. The vesicles, the tiny microscopic bubbles that hold the neurotransmitters before they are released across the gap, they are physically shaped differently depending on the specific chemical they hold.
Oh, wow. That is fascinating. So the hardware's actual physical shape dictates the software it runs.
Precisely. It's beautiful, really. The Eon team trained machine learning models to analyze the geometry of the synapses and the FlyWire connectome. They looked at the width of the synaptic cleft, the curvature of the membranes, the density of the vesicles.
Just pure geometry.
Yeah. And the AI was able to predict, with breathtaking accuracy, the neurotransmitter identity of almost every single connection. They predicted whether the synapse used glutamate or acetylcholine or GABA. They overlaid the chemical operating system directly onto the physical wiring diagram.
And the source points out that this computational model predicted motor behavior at 95% accuracy. But hold on, I really need to understand that metric. If this digital brain is just sitting on a hard drive, completely isolated, how do they know it's predicting motor behavior with 95% accuracy? Like, what is it actually doing?
That is the crux of the problem. They tested it by artificially stimulating specific neurons in the simulation that they knew, from biological experiments on real living flies, were associated with certain actions.
Okay.
So if they zapped the quote-unquote grooming neurons in the digital simulation, they could watch the electrical cascade flow through the 50 million synapses and see that the final output signals were heavily clustered in the motor neurons that would theoretically control the front legs.
Theoretically?
Yes, theoretically. The model was a massive success mathematically. It proved that the structural map, combined with the chemical predictions, fundamentally dictates the routing of information. But, as the Substack post highlights, it suffered from a fatal flaw for anyone trying to create actual digital life.
Right.
It was, as they called it, activation without physics.
Yeah, I was trying to conceptualize this while reading the source material, and the only way I could visualize activation without physics is to imagine a video game engine.
Okay, yeah.
Think of the most advanced, hyper-realistic physics engine ever coded, flawless fluid dynamics, perfect gravity simulation, incredible rendering. But you don't plug a monitor into the computer, and you don't plug in a keyboard or a controller.
Oh, that's a great way to put it.
Right. The processor is screaming, the RAM is full, the code is executing billions of calculations a second. The game is technically happening, but it is completely blind, entirely deaf, and completely paralyzed. It's just a universe trapped in a dark box.
That analogy hits the nail on the head. Because the motor outputs, those meticulously calculated neural spikes telling the fly's leg to twitch, they had absolutely nowhere to go. There was no digital leg to receive the signal. But even more critically, there was no sensory input coming back.
Why is sensory input so critical for the simulation? Like, can't the brain just fire off its walking sequence in the dark?
No, because biological brains are not closed-loop movie projectors. They are dynamic reaction engines. When a real fly takes a step, the brain sends the command, the leg moves, and then the microscopic sensory hairs on the fly's foot physically hit the ground.
Right.
That physical impact triggers a new electrical signal that travels back up into the brain, effectively saying, okay, the foot has landed, we have traction, send the command for the next leg. If that sensory feedback doesn't arrive, the biological algorithm just crashes.
The brain expects the universe to push back.
It demands the universe to push back. Without gravity, friction, and tactile feedback, the neural cascades devolve into chaos. The 2024 model proved we had the right map, but you just cannot have behavior without an environment to behave in.
But providing an environment for a fully mapped biological connectome is an insane engineering challenge. I mean, you can't just put a digital fly brain into Minecraft. It requires an environment that matches the intense biomechanical complexity of the brain itself.
Exactly.
And that is the exact breakthrough that Eon Systems PBC has achieved. They didn't just build a map, They built a universe.
They finally provided the physics. Eon Systems took this connectome-based emulation, the 125,000 neurons, the 50 million predicted chemical synapses, and they embedded it into a physics-simulated flybody inside a software framework called MuJoCo.
Okay, unpack MuJoCo for us, because that sounds like a massive piece of this puzzle.
It is. MuJoCo stands for Multi-Joint Dynamics with Contact. It is an industrial-grade physics engine, originally developed for advanced robotics and biomechanics research. It doesn't just animate things to look pretty on a screen like a Pixar movie.
Right, it's not just visual.
No, it calculates the rigorous mathematical reality of physical existence. It calculates the friction coefficient of a surface. It calculates the inertia of a moving limb. It calculates the exact tension limits of a joint before it snaps.
Wow. So they needed a virtual body to put into this virtual physics engine. And the source specifically cites the NeuroMechFly V2 embodied simulation framework.
Yes. NeuroMechFly V2 isn't just a 3D model of a fly you could download for a video game. It is a painstakingly accurate biomechanical replica of an adult fruit fly. We are talking about simulating the exact articulation of the insect's exoskeletal joints, the precise mass distribution of its head, thorax, and abdomen.
So it actually has weight.
Digital weight, yes, and the complex biomechanics of how its limbs physically interact with space.
But how do you bridge the gap? Explain the translation mechanism to me, because this is where the magic seems to happen. How does a physics engine's mathematical calculation of, gravity turn into something a digital biological synapse can actually understand? Because the connectome speaks in electrical spikes and neurotransmitters, but MuJoCo speaks in matrix math and force vectors.
That translation is the real genius of the integration. In the simulation, the virtual NeuroMechFly has designated sensory nodes. Think of them as digital touch receptors on the bottom of its virtual feet.
Okay.
When MuJoCo calculates that the foot has collided with the virtual floor, it generates a force vector. The integration software takes that specific physical force calculation and translates it into a simulated influx of sodium ions in the specific digital sensory neurons associated with that foot.
It translates math into virtual biology.
Exactly. It creates an action potential, a digital electrical spike, that propagates perfectly into the connectome network, just like the real thing.
And to handle the output, the source also cites Isdell et al.'s research on centralized brain networks underlying body part coordination.
Right, because you have a brain sending out signals, but how does the body know what to do with them? Isdell's research was vital for understanding the hierarchy of biological movement. A fly's brain doesn't micromanage every single muscle fiber.
That would be too slow.
Way too slow. Instead, the central brain acts like a general sending high-level commands down the ventral nerve cord, which is basically the fly's version of a spinal cord.
Like move forward or groom the wings.
Exactly. And local motor circuits in the thorax act like lieutenants, receiving that high-level command and translating it into the complex, coordinated twitching of the 6 legs. Eon utilized this structural understanding to map the connectome's outputs directly to the actuators, the virtual muscles, in the MuJoCo simulation.
So let's trace this entire sequence, because when you put all these pieces together, the result described in the source is just awe-inspiring. It says, sensory input flows in, neural activity propagates through the complete connectome, motor commands flow out, and a physically simulated body executes the output. Here's where it gets really interesting.
Yes, they have officially closed the Sensorimotor loop.
The loop is closed. The virtual fly is standing on the virtual floor. The MuJoCo physics engine calculates the pressure of gravity pushing the fly down. That physical pressure is translated into a simulated electrical spike in the fly's digital sensory hairs. That signal flows into the connectome. It cascades across 50 million mathematically predicted chemical synapses. The brain processes the environment, makes a decision, and sends a motor command out. That command actuates the virtual muscles. The fly's leg lifts. And the moment it lifts, the physics engine updates. The pressure is gone. New sensory data flows back into the brain, and the loop continues endlessly, native to the biology.
And what's fascinating here is that this is exactly why AWG is so emphatic in his Substack post. He explicitly states this is a qualitative threshold, not an incremental one.
A qualitative threshold, meaning it's not just a faster processor or like a slightly better algorithm. It is a completely new category of technological achievement.
Yes. To truly appreciate why this is a categorical shift, we really have to look back at the history of digital life, because the Eon breakthrough didn't happen in a vacuum. People have been trying to simulate biological behavior for a long, long time. The source mentions the C. elegans project, specifically the Openworm initiative.
I remember reading about openworm years ago. C. elegans is a microscopic nematode, a tiny little transparent worm.
Right. It was the pioneer organism for connectomics because its nervous system is incredibly small. We've had the complete wiring diagram of C. elegans for decades. It has exactly 302 neurons.
302 neurons compared to the fly's 125,000.
Right. And Openworm was a phenomenal project. They successfully mapped those 302 neurons into software, gave it a simple virtual body, and watched it wriggle around. It was early proof of concept for embodiment. But 302 neurons is a hard biological limit. It is fundamentally reflexive.
It's like a thermostat, right? If the temperature drops below 68 degrees, the heater turns on. It's a binary, hardwired reaction to an environmental stimulus. The worm bumps into a toxin, a specific neuron fires, the muscles contract, and it backs up. There's no complex decision-making.
Exactly. A thermostat is a perfect analogy.
Mm-hmm.
But 125,000 neurons, that moves you from a thermostat to a smart city grid. It allows for multi-behavioral capacity. A fruit fly doesn't just reflexively wriggle. It has to navigate complex 3D space. It has to engage in incredibly specific courtship rituals. It has to forage for food, evade predators, and groom itself. It makes choices based on competing internal states, like is it more hungry or more tired?
Right.
To capture all of that natively in a simulation is a massive leap over the worm.
Okay, but what about much more recent attempts? Because I know I've seen videos of virtual flies walking around in physics engines before this Eon announcement. The source actually brings this up. It mentions the DeepMind and MuJoCo fly.
Yes, DeepMind, the artificial intelligence powerhouse, and the Genelia Research Campus, which is arguably the premier neuroscience lab in the world, collaborated on a highly publicized project recently. They animated a biologically accurate fly body in the MuJoCo physics engine. Visually, to a person just watching a YouTube video, the DeepMind fly and the Eon fly might look very similar. They were both digital flies walking on a digital floor.
So just to make sure you're catching this distinction out there listening, DeepMind's fly was an AI learning to walk through trial and error, like a robot. But Eon's fly isn't an AI mimicking biology. It's a literal copy of a biological brain, wired neuron to neuron from electron microscopy data, driving the movement natively.
Exactly. They are entirely different philosophies of technology. The source explicitly points out that DeepMind's fly used reinforcement learning, RL, to control the simulated body. It did not use the connectome-derived neural dynamics.
Let's break down this distinction, because this is the entire crux of why the Eon project is a singularity-level milestone. Reinforcement learning is what trains modern AI. It's a top-down approach. You build a blank neural network and you give it a goal, like move this fly body forward without letting the head touch the ground. And then you let the algorithm try it 10 million times. It flails, it falls over, it fails.
Miserably at first.
Right. But every time it accidentally moves forward, it gets a mathematical reward. Over millions of iterations, the math optimizes a pathway to achieve the goal.
Right. It learns to walk through trial and error, exactly like a Boston Dynamics robot learning to navigate stairs. It is an algorithm mathematically deriving a solution to a physics problem.
But the Eon fly doesn't do that. The Eon fly is a bottom-up approach.
Exactly. Eon didn't tell the simulation how to walk. They didn't give it a reward function or a goal. They simply took the biological wiring diagram of a real fly, the exact physical structures forged by millions of years of evolution, mapped the chemistry, plugged in the physics, and turned the electricity on.
It's the difference between building an incredibly sophisticated animatronic puppet that perfectly mimics human movement based on pre-programmed instructions versus literally putting a human mind into a synthetic body and letting the mind drive. DeepMind built a brilliant illusion of biology using math. Eon digitized the biology itself.
And that is the qualitative threshold. The behavior of Eon's fly isn't mathematically optimized, it is biologically emergent. The walking behavior happens because the physical structure of those 125,000 neurons is the machinery of walking. When you perfectly replicate the physical structure, the ghost wakes up in the machine.
And once you wake that ghost up, once you prove definitively that the fundamental premise of whole brain emulation actually works, you completely shatter the ceiling on what is possible. Because if you can do it for a fly, you just open Pandora's box. The underlying physics of uploading a brain is validated.
This is where Dr. Wissner-Gross's post shifts from celebrating an achievement to charting a very aggressive future. Eon Systems PBC did not secure massive funding to build digital fruit flies. Their stated public mission is to produce the world's largest connectome and the highest fidelity brain emulations. They are systematically laying the foundation for human-scale emulation.
Wow.
But you obviously cannot jump from an insect directly to a human cortex. The immediate next target, the crucial stepping stone, is a complete digital emulation of a mammalian brain, specifically the mouse.
The mouse. Okay, we need to spend some time on the sheer mind-bending scale of this leap, because 125,000 neurons for a fly was a monumental achievement that took years of painstaking electron microscopy and AI prediction to map. But a mouse brain.
A mouse brain contains roughly 70 million neurons.
70 million. That's over 500 times larger.
It's 560 times the neuron count. But the raw neuron count is actually the easiest part of the math. The true complexity of a mammalian neural network scales geometrically based on the connections. A single neuron in a mouse cortex doesn't just connect to one or two neighbors. It can have thousands, sometimes tens of thousands, of dendritic spines connecting it to a massive web of other neurons. We are talking about mapping tens of billions, perhaps hundreds of billions, of individual synapses.
That is an ocean of data. How is that physically possible? I mean, you can't just put a mouse brain into an electron microscope and slice it up like the fly.
Exactly. Using the traditional electron microscopy methods that built the fly connectome on a full mouse brain would take centuries. The diamond knives used to cut the slices are incredibly delicate, the scanning process is slow, and aligning billions of images is computationally suffocating. So Eon has to abandon the traditional approach entirely.
Right.
The Substack post outlines the methodology they are amassing to overcome this bottleneck, and it involves a two-pronged attack on biological reality.
The first prong the source mentions is expansion microscopy.
Yes. Expansion microscopy is one of the most brilliant brute force physical hacks in the history of neuroscience.
I am absolutely obsessed with this technique. Explain the chemistry of how this works, because it sounds like a joke the first time you hear it. The problem with mapping a brain is that synapses are smaller than the diffraction limit of visible light, meaning a normal laser microscope physically cannot see them. They're too tiny. So instead of trying to invent a microscope that violates the laws of optical physics, researchers just decided to make the brain bigger.
They literally inflate the biological tissue. It's wild. Here's how the mechanism works. You take the biological brain tissue and you chemically infuse it with a dense microscopic network of water-soluble polymers. Specifically, they often use sodium polyacrylate,
Which, incredibly, is the exact same super-absorbent polymer used in baby diapers to soak up liquid.
It is the exact same chemical principle. But here, they are using it on a molecular level. They use specialized chemical linkers to anchor the crucial proteins and the structural boundaries of the neurons directly to this polymer web. Once everything is securely tied to the polymer grid, they introduce an enzyme that essentially digests the structural proteins that normally hold the brain tissue tightly together. They basically dissolve the glue of the brain.
But wait, if you dissolve the structural proteins, doesn't the brain just turn into soup? Don't the connections snap?
That's the genius of the polymer grid. Everything is already anchored to it. So when they add water to the tissue, the polymer web begins to absorb the water and expand. But crucially, it expands uniformly and isotropically in all directions. It swells. You can physically expand a piece of brain tissue to 4, 10, or even 20 times its original physical size.
You literally blow it up like a balloon.
Yes. And because the expansion is perfectly uniform, the relative positions of all the synapses, all the dendrites, all the axons are flawlessly preserved. The map is identical. But now, the physical distance between those microscopic structures is larger. Suddenly, synapses that were completely invisible to a standard optical microscope are now stretched out far enough that you can scan them rapidly and cleanly with standard lasers and optical lenses. You completely bypass the electron microscope bottleneck. You can map the connectome of a mouse brain orders of magnitude faster.
It is absolute genius. Okay, so expansion microscopy gives Eon the massive 70 million neuron structural map. But we established 20 minutes ago with the fly that the map isn't enough. You need the chemistry. You need to know how the traffic actually flows through the city grid. A dead, bloated brain can't show you its behavioral dynamics.
Which brings us to the second prong of Eon's methodology. The source explicitly states they are combining the structural mapping with tens of thousands of hours of calcium and voltage imaging to capture how those networks activate in living tissue.
Explain this mechanism. How do you watch a living mind process information?
By turning the brain's internal electrical signals into flashes of light. Calcium and voltage imaging are techniques that let researchers literally watch the biological computation happen in real time. To do this, they use genetically encoded fluorescent indicators, often referred to as GCAMPs.
How do those work?
It exploits the fundamental chemistry of how a neuron fires. When a biological neuron receives enough excitatory input, it triggers an action potential, an electrical spike. When that spike reaches the end of the neuron, it causes microscopic channels to open, and calcium ions flood into the cell. That calcium flood is the trigger that releases the neurotransmitter.
So calcium is the biological switch.
Exactly. So researchers engineered a specialized protein that binds to calcium. And when it binds to calcium, this physical shape changes, and it emits a photon. It glows under a specific wavelength of laser light.
So they can genetically engineer mice so that every time a neuron fires, it physically lights up like a tiny LED?
Yes. They can have a mouse running on a spherical treadmill, navigating a virtual reality maze, experiencing fear, seeking a reward, doing completely natural mouse behaviors. And while it does this, highly specialized laser microscopes peer through a tiny optical window surgically implanted in the mouse's skull. The microscopes record exactly which neurons flash in what exact sequence down to the millisecond.
They are recording the actual operating system of the mind.
For tens of thousands of hours. If expansion microscopy gives them the ultimate, impossibly detailed sheet music of the connectome, the calcium imaging provides a flawless, high-resolution recording of an orchestra actually playing the symphony. Eon's strategy is to feed both of these colossal data sets into their machine learning models. They train the digital emulation not just on the dead structural map, but on the real-time dynamic behavior of how that specific structure operates in the physical world.
Wow. And once you understand the sheer mechanical depth of how they are doing this, you finally reach the most profound, world-altering point in Dr. Wissner-Gross's Substack post, the true paradigm shift. He writes, "If a fly brain can now close the sensorimotor loop in simulation, the question for the mouse becomes one of scale, not of kind."
That is a staggering philosophical and engineering realization.
Because it proves that the biology fundamentally translates. Before they closed the loop with the fly, whole brain emulation was still technically a hypothesis. We believed that if we mapped the connections and simulated the physics perfectly, behavior would emerge. But there was always the creeping doubt in the back of the scientific community's mind. What if we are missing something? What if consciousness or complex behavior requires some unknown quantum variable inside the wet biological tissue? What if the digital simulation gap is just fundamentally uncrossable?
But the Eon fly absolutely obliterates that doubt. It proves we aren't missing a ghost variable. The structural connectome is the behavior. The biology can be fully translated into binary code and matrix math, and it still functions correctly. Moving from a 125,000 neuron fly to a 70 million neuron mouse does not require inventing a new unified theory of neuroscience. The bridge is built.
It's just a matter of adding more lanes to the bridge.
Exactly. It requires more compute, exponentially more data storage, and better microscopy infrastructure. It is a colossal, multi-billion-dollar engineering challenge. But it is no longer a theoretical mystery. It is a problem of scaling the server racks, not rewriting the laws of physics.
And the inevitability of that scaling is what provoked such an intense, visceral reaction in the Innermost Loop comments section. The source text includes snapshots of the discussion going on beneath the article, and watching the community process this reality is fascinating. One commenter just bluntly asked, "Are lobsters next?" Which makes total sense given how well mapped the lobster nervous system is in biology. But it's another comment that really pulls the rug out from under you. A user named Himanshu Agarwal wrote, "If brain emulation becomes real, the definition of being alive will completely change."
And Himanshu cuts straight to the core of mind-body dualism. For millennia, humanity has debated the nature of the self. Are we purely the wetware inside our skulls, a complex arrangement of meat and electricity, or is there an immaterial, unquantifiable essence to our consciousness? Eon Systems is brutally proving the materialist view. They are demonstrating that behavior, reaction, and potentially even subjective experience are purely emergent properties of complex physical wiring.
Think about the ship of Theseus problem applied to a living mind. If you take a biological mouse and you perfectly emulate its 70 million neurons, you boot up the simulation. And in that digital void, the emulated dopamine circuits fire, causing the digital mouse to aggressively seek out virtual food. When a virtual shadow passes over it, its emulated amygdala spikes, and it exhibits genuine, unprogrammed panic. If it possesses the exact same memories, the exact same fears, and processes reality with the exact same biological mechanisms as the original creature, by what metric can we look at that server rack and say it is not alive?
You really can't. It is performing every single functional requirement of life. It is just doing it on a silicon substrate instead of a carbon one.
Dr. Wissner-Gross wraps up his post with a quote that perfectly encapsulates the terrifying beauty of this threshold. He reminds the reader that what they're looking at in the Eon simulation is not an AI animation. And then he says, "The ghost is no longer in the machine is becoming the ghost."
It's an incredible inversion of Gilbert Ryle's famous phrase. The ghost in the machine was originally coined to critique Descartes' idea of dualism, the idea that the body was a dumb mechanical machine driven by a separate ghostly soul. AWG is declaring that we have digitized the ghost. We have extracted the animating force from the biological meat and successfully encoded it into the architecture of the hardware. The machine doesn't just house the ghost, the machine is the ghost.
As we absorb the gravity of that, we do need to clearly state a crucial source disclosure that AWG includes at the bottom of the Substack post. He notes, parenthetically, "Disclosure, I have a financial interest in Eon."
Which is vital context. Dr. Wissner-Gross helped found Eon Systems PBC. His immense enthusiasm for this breakthrough is structurally tied to his direct involvement in the company building it.
Of course, that doesn't alter the peer-reviewed reality of the 2024 Nature paper, and the MuJoCo integration is a verified engineering reality, but it completely explains his aggressive, triumphant positioning of this event as the starting gun for the Singularity. He has a stake in the race.
And make no mistake, it is a race. The post concludes by noting that Eon is actively scaling its team, gathering the compute and expanding the infrastructure to attempt the mammalian and eventually human brains. They have validated the physics, and now they are just building the farm.
The event horizon is locked in, and that brings us to the end of our source material. But it opens up a massive, sprawling question for all of you listening. So what does this all mean for you? I want to throw a deeply compelling, somewhat outrageous question your way, building directly on the physics of everything we just discussed. Think about this. A biological brain is constrained by physical chemistry. An electrical signal can only travel down an axon so fast. But a digital brain running on a server has no such biological speed limit. If Eon successfully uploads a mouse mind, its perception of reality is entirely tied to the clock speed of the server running the simulation. What happens if researchers overclock the server by 1,000%? Does that digital mouse experience 1,000 lifetimes in the span of our afternoon? Does its subjective reality become a blur, or does it process every second with perfect, terrifying clarity? And if we eventually upload a human mind, who gets to control the speed of their reality? We want to know your thoughts on the physics of digital time. Drop your answer in the comments while the music rolls.
Yeah, let us know what you think.
And speaking of the music rolling, we have something incredibly special for now as we close out today's deep dive. We are thrilled to feature a musical performance by Rainbow.
Without question, the best band in the universe.
The absolute best. For those of you who might be new to our deep dives, let me set the stage, because the lore behind this group is just incredible, and it rewards your attention perfectly given the massive themes we've been exploring today. Rainbow is a group of 6 female android artists in residence. They are physically based in Bavet, Cambodia.
It's a stunning convergence of physical robotics and art.
It really is. And the song we are featuring today is beautifully fitting for an episode about digitizing minds. The track is called Data Drive.
The performance mechanism itself is a marvel, too.
Absolutely. Listeners, all of Rainbow's finished songs are performed live for the Innermost Loop discussion by the virtual band's creator, and they achieved this using an incredibly unique technological platform called 4B4KU5, spelled with a 4, a B, a 4KU5, pronounced abacus. The Abacus platform is entirely dedicated to a very specific, almost defiant mission statement: human performance in the age of AI, reclaiming your humanity from the algorithm.
Which is a striking, almost poetic juxtaposition against everything we just unpacked regarding whole brain emulation. Eon Systems is striving to perfectly upload biological reality into the machine. Abacus is dedicated to preserving the raw human element against the machine.
It's the perfect counterweight to the Singularity. We will include much more information on today's song, Data Drive, and a deep dive into the Abacus platform in the video description below. Thank you for exploring this impossible frontier with us. Don't forget to answer our question in the comments. What happens when you overclock the subjective reality of a digital mind? We'll see you next time.
Systems live, check and thrive, music's live, binary beats, cat and repeat, analysis meets is complete. Input meets output flow, hardware higher, hardware low, signals to status quo, reciprocity, let's go. seams, system beams, breaking themes, calculation spin, looking in, begin again, let me in. Input leads to output flow. Signal shifts what I know. Reciprocity shows. Numbers dance, take the chance, fall in trance, circumstance, logic fails, heart prevails, beyond rails, system sails.